Hi, welcome back to Engineering 255 Statics. We are going to continue discuss about the moment. Previously, we defined what is a moment. Also, we define uh, couple moments which are caused by two forces in the opposite direction, but they have a distance. In this video, we're going to talk about force system resultants, and we are going to see how we can simplify a force to a force and couple system. And we're going to show you some of the example. So let's take a look. The objectives for this video is to show you how we can find out the effect if we move a force. You can move a force in certain different way, and you will find out once we move the force, we can find an equivalent system. The system is going to be composed by force and the couple. So in general, if you apply a force on a system, we can represent as a force and moment system at any point. To show you what we mean that you can move a force and you can simplify that into a force couple system, think about this example right here. If I hold a bar and we apply a force and the force is horizontal to the bar, and we can move this force at any point along the bar. You can move the force to uh, the point that I hold the bar, or you can put it at the tip of the bar. They will have the same effect. So they are equivalent. So this system is the same as this system. What if you have a force which is perpendicular to the bar? Well, this is going to be different because when you apply a perpendicular force, this force not only will try to make this force, make this bar to be bended, it also try to make this bar rotate. So the experience of this bar will not only going to have a force but also have a rotation tendency, and we can represent this force by moving this force to the starting point like this one here. But when you move that force to here, and there's a moment will be created due to the force times the distance when you move this one to here, and it will be equivalent system. We're going to show you how this idea is created in the next slide. So to begin with this idea that how do we simplify a system that has a force and couple? And what is a couple? A couple meaning two forces at opposite direction and with the same amount of force, right? So if you apply any of the force to an object and you have a moment that apply to the object at certain places, and this object is going to be a rigid body, then we can combine all of this to certain point of the object, and we can simplify that, only represent that by a summation of the force and also the net moment around this point. And that's the whole idea. So how can we find an equivalent system that had the same kind of external effect, this effect including the force and the moment. So force will make things accelerate and the moment try to make things rotate. Here we're going to explain how we come up with this idea. So let's start with a simple case. If you apply a force that is parallel to the bar and the force can slide along this bar, so I can make this force to be at the beginning, I can make this force to the middle, I can make the force to the starting point of the B. So it can be any point, but it's going to be the same amount of the force. And that's what we mean. This is a sliding for a sliding vector. Okay. Um, that idea is that if you wanted to see how this one can transition to this one, you can add at the holding point with a pair of the force, and this pair of the force had the same amount but have the opposite direction. So it's actually you are giving zero net force, right? If you give zero net force at here, and that's cancel out this negative F at here and the starting force at here, then what you left is this force right here, and which is this result shown at here. So these two are going to be equivalent. What about moment? What about the force is not along the bar? What about the force is perpendicular to the bar, which is this case here? We apply force at the tip at the point of A. There's a distance of D from the holding point of B. That's at two forces at the starting point of the B, like this. They are same amount, they are opposite direction, so F and negative F. Then we can cancel out um, these two because these two are a couple. These two are the same amount of the force in the opposite direction. And we talk about this when you have a couple, you create a couple moment. The couple moment at any point is going to be the same amount. So that couple moment is the couple moment will try to make this one rotate in this direction, which is a clockwise direction. It could be the couple moment at here. It could be the couple moment at here. It's going to be the same amount. So we replace this couple by its moment. So this is how we come up with this idea. You can represent a single force at the point of A and replace that be an equivalent system with a force at the beginning point and a couple moment at that same point. And the moment, as we said, is a free vector because you can move anywhere. It's going to create the same effect. But these two are going to be equivalent. So we have an equivalent system that will create the same effect to the subject. With that in your mind, then we're going to kind of summarize what this idea is. When you have any of the system and you apply the force and the moment to an object, so this is an object. If the object is a rigid body, we can sum the forces together and we can sum the moment um, by calculating the moment due to the force and the moment that is applied to the system, and you sum it all together. This is going to be the net moment that is created. So over here, summation M of C represent the couple moment due to a pair of the forces, and summation moment of all represent the moment at the uh, the reference point or the common point that you are referring to. Um, so let's just look at an example. You have horizontal bar right here actually is supporting two light, and these two traffic light all have the different weight, W1 and W2, and they are at a different position away from this pole at here. So there's a D1 and D2. The weight is a force, so if we ignore the weight of the bar itself, then the traffic light will apply a force downwards, and which is perpendicular to this supporting rod here. Because they're perpendicular, they're going to create a moment. And so then we can move these two by summing them together and put them to be the starting point of the supporting point of O. This will be the resultant force at the point of O, when you move that, you have to also put the moment, because you move the force that is perpendicular to the rock, so you have to have the moment of W1 times D1 and W2 times D2. These are what we call the resultant moment with respect to the point of O. That is MR of O. So that is what we means when you have this kind of system, you can make an equivalent system in this way. And well, this is the case that you only have Y component. If you have X component, then you are going to do the same thing. You sum the net force in the X direction and move that force to this point. If you do so, then the moment will be a little bit complicated because the X component might also have a moment that will affect to the point of O. So let's look at how we simplify force and couple system in a real situation. Over here you can see the case of A. We have three forces, right? F1, F2, F3. And we have a reference point, which is the point of O. The plane is on the XY plane and vertical direction is the Z direction. When you want to find an equivalent system, you simply just move all the forces all together to the point of O. You sum all these forces together. So you have F1 minus F plus F3 minus F2. That is the net force. But you also, when you move the force, you also need to write down the moment with respect to this point O due to each one of the force. So the summation of the moment that at the point O is the net moment caused by this one, and this one. You are referring to this point O. So when you do this, you need to represent F1 and F2 and F3 in a vector form, which will be easier for you to find out what is the net moment. Okay, so um, so you can do that by summing all them together. Let's look at an example to show you how we actually do the calculation. And here we have a bar which is horizontal. The endpoint A is fixed to a wall, and in the middle of the bar we have 3 points. We apply forces at a different location. The first one is 200 pounds, that is 3 feet away from the endpoint. And then another 3 feet, you have an angled force going downward to the right, and it's 100 pounds. And at the end point, you have 50 pounds with an angle of 30 degrees with respect to the vertical direction. We want to find if we move these three forces to the endpoint of A, then what is the equivalent force system? Okay, so that is that what if we make this case to a different case, and that different case is going to be, here is the A, and this is the bar, and we're going to represent this one um, with a net force that has X and Y and also has a moment at here. So you have f of x, f of y, f of x, and this is going to be the net moment of A. Okay, now let's see how we solve this problem. So the first thing you do is to find the net force. So you have three different forces. We can sum them all together. Um, for this force at here is just simply a y direction, right? So I have f of y, which is 200 pounds. this one you have to decompose, this one you have to decompose. So we decompose that, and we just sum it all together and here. So let's look at the x direction. The x direction can be contributed by this one here and this one here. How much is due to this one? For the fx of this one, that is this much. This is equal to 100 times 3 over hypotenuse, which is 5. This has a y component, which is 100 times 4 divided by 5. For this one here, we have x component, that is 50 times cos, if you want to do sine angle 30, that will be this much amount, right? So that will be sine 30. You can also do cosine 60, that will be the same. For the y component is going up, and this will be 50 times the cosine 30 degree. So, and this will be negative because this is going down. So if you look at the x direction, for the x direction, we have this one here, we have this one here, and that's it. So you have two things you added together, and that's this one and this one, which is this one and this one. And if you look at the y direction, we have 200, which is right straight up. This is 200. This one is due to this one here, and this one is this one here, and it's negative, right? So you can sum these force. So x is 85, y is 163.3, and the moment, when you do the moment, you're going to find a moment that will make this one rotate. So 200 pounds is going to make this rotate in this direction, and the amount of the moment due to this force is going to be 200 times 3 feet. So this is a 200 times 3 feet because of the first force right here. If we look at the second force, which is this force right here, this component is not going to create any of the moment because this is parallel. This actually go through this point. There's no distance, right? You have to have the force with the distance between the reference point to the force action line, and the action line actually go through that, so there's no D. The only force will make a moment is this one here, and this one is going to create the object to rotate in this direction, which is a clockwise direction. Clockwise direction, we will make it negative. So this is the green one right here. You have negative 100 times 4 over 5, which is this force, and you multiply with the distance from here to here, which is 6 feet. So this is 6 right here, and that's negative. The last one that we're looking at is the this one here, and this one, you again, the x direction is not going to create any of the moment. This one will create the moment, and the amount of the force is going to be 50 cosine 30 degree. 50 cosine 30 degree. The distance is going to be 3 is going to be 9, and you sum it all together. This is the net moment will create at this point A. So if we draw an equivalent system, and this is going to be the equivalent system, you have the amount of Fx 85 pound. You have F of y positive number, so it's 163.3 pounds. You also have a moment counterclockwise, so this is the moment counterclockwise 509.7 pound and feet. And that is the equivalent system to the system on the top. Okay, so once we find a component of the resultant force, we can represent the amount of the resultant force. So remember this F of R, just get a pen. This F of R is a vector and it's represent as the magnitude of the force with an angle. And we can do the calculation if you know each one of the component, and you can find the resultant force magnitude and also the angle for that resultant force. So we start with a system like this. We have a force here, we have a force here, we have a force here. And we try to represent this force in this way, which is the previous slide. So we represent this as the net force at this endpoint with the moment at here. And the question trying to ask you is this: can I move the force such that I can have only the force acting on the bar, but it has the equivalent result? And you can do that if you shift this one to certain distance at here, and we know the force is going to have F of R with an angle of theta. So I going to shift this one to this location with the same effect of the resultant force and angle, but there's no moment at here. And you are doing like a opposite way. So we were starting with a force move to a certain place and you create a force and a moment. Now we are doing like opposite way. So we are given this net force and we're gonna say, oh, I also know how much net moment that is. Can I move this one to a certain place? That is how this was generated. So we want to find the distance of this one here. And it's the same thing like what we were doing. If you look at this force, X component is not going to create any moment. Only the Y component will create a moment. And the force of the Y component is going to be F of R of Y. And that force is going to try to make this one rotate counterclockwise. So how much of the moment it will create it? It will be the Fry times the D. So this moment of this moment is equal to Fr times Y, Fr of Y times the D. And we want to find D, so that's how we got this equation. We try to find D, we divide both and both sides by the Fry, and then we can find what's the distance. If I move the force to here, then I simply represent that force. I don't need to have any of the moment. And that is the whole idea about the equivalent system. I know this is not an easy topic, so I hope that you do some of the homework to understand this idea. That is about it for this video. Okay, so that is what we need to tell you.